Hello, and welcome to Differential Equations. This is lecture 37, the Laplace equation. Last time we talked about the wave equation. This time we're going to take another look at the wave equation and then the Laplace equation, which is a stationary version of the wave equation or of the heat equation. Let's consider the wave equation with Dirichlet boundary conditions on the interval 0L, and this time with arbitrary initial conditions with respect to time. So that means that our equation is two derivatives of u with respect to t is equal to c squared times two derivatives of u with respect to x, satisfying that at the endpoints of the interval and for all time, the solution vanishes, and at time equal to 0, our function is equal to f of x, and the derivative of our function is, let's say, g of x. So as before, Dirichlet boundary conditions lead to the Fourier sine series. So let's look for a solution of the form u of xt equal to the sum n goes from 1 to infinity of some coefficients, so beta n of t times sine of n pi over Lx. Right? So by doing this, we've arranged for the boundary conditions to hold, and so we just need to think about the initial conditions and, of course, the equation. Let's go ahead and expand f and g in Fourier sine series. So f of x is the sum n goes from 1 to infinity of, let's say, phi n times sine of n pi over Lx. And g of x is the sum n goes from 1 to infinity of, let's say, gamma n sine n pi over Lx. If we plug this into the equation, then we get, well, take two derivatives with respect to t, right? And since we've decided to look for u of this form, this would look like the sum n goes from 1 to infinity of beta n double prime of t times sine of n pi over Lx. We want that to equal c squared, the second derivative of u with respect to x. So that would look like c squared times the sum n goes from 1 to infinity, beta n of t times minus n pi over L squared sine n pi over Lx. Right, and then we don't have to worry about the boundary conditions, but we do need to think about the initial conditions. So u of x0 is sum n goes from 1 to infinity of beta n of 0 sine n pi over Lx. And we want that to be equal to f of x, which is the sum n goes from 1 to infinity Vn sine of n pi over Lx. And the derivative of u with respect to time at time 0. So this would be the sum n goes from 1 to infinity of beta n prime of 0 sine n pi over Lx. And we want that to be equal to g of x, which has this Fourier sine series. Right? So that's what the equation becomes. And so each beta n satisfies, right? Just comparing coefficients of sine n pi over Lx, right? We have this boundary value problem, actually initial value problem for this ODE. The general solution of this equation is beta n of t equals some constant times cosine of c n pi over L t plus some coefficient times sine c n pi over L t. And when we plug in the initial conditions, we find beta n of 0. So beta n of 0, sine of 0 is 0. So we just end up with a, and that has to be phi n, whereas beta n prime of 0. So what if I differentiate this? I'm going to have a sine, which at 0 would be 0. So it's only when I differentiate this that something shows up. And I would get b c n pi over L, and then cosine of 0, which is 1. And that should be equal gamma n. So that tells us that b is equal to gamma n divided by cn pi over L. So we've found beta n of t. It's phi n cosine of cn pi over L t plus gamma n divided by cn pi over L times sine of cn pi over L t. And we've found the solution of the equation. U of xt would be the sum n goes from 1 to infinity of phi n cosine of cn pi over L t plus gamma n over cn pi over L sine of cn pi over L t. All of that times sine of n pi over L x. Okay, so that's the general solution to the wave equation with Dirichlet boundary conditions. One thing that's worth noticing in contrast to the heat equation, where we typically had coefficients like e to the minus sigma n pi over L squared times t, which decay as t goes to infinity. For the wave equation, the coefficients are trigonometric functions of t. And don't really decay or grow as t goes to infinity. Right, so that's a big difference between the heat equation and the wave equation. All right. The final partial differential equation that we're going to look at is the Laplace equation, which arises as the stationary equation, meaning independent of time. For either the heat or the wave equation. Thus, in one dimension, the Laplace equation would just say two derivatives with respect to x is equal to 0. In two dimensions, the Laplace equation would say two derivatives with respect to x plus two derivatives with respect to y is equal to 0. In three dimensions, you would have two derivatives with respect to x plus two derivatives with respect to y plus two derivatives with respect to z equal to 0, etc. This is an extremely important equation in both mathematics and physics. It shows up, for example, in electrostatics, in gravitation and general relativity, and fluid dynamics. Of course, in each of those settings, things might be a little more complicated than the equation the way we've written it, but something very similar, something like this, shows up. Let's do, as an example, the Dirichlet problem for a rectangle. Let's solve, or let's consider at least, the equation. So let's look at the two-dimensional case. On the rectangle, so where x is between 0 and a, and y is between 0 and b. Subject to the boundary conditions. Okay, so here, in contrast to the heat and wave equation, when we talk about the Dirichlet problem, we're not really interested in just setting the boundary conditions equal to 0. Right? If you just set the boundary conditions equal to 0 for the Laplace equation, you typically don't have any interesting solutions. Instead, we want to prescribe the values of the function on the boundary. So if we're thinking about the rectangle, what we want to do is, for example, at the left boundary, we want to fix some function w of y. At the top boundary, we want to fix, so this would be when x is varying and y is at the top. So let's say that that was some function n of x. At the bottom, you have n of u of x comma 0, and let's say that's s of x. And here on the right boundary, so use u of a comma y, you want that to be some function e of y. So this is the sort of thing we want to know. I tell you what the function should be on the boundary, and I tell you that it satisfies this equation on the interior. I want you to tell me what is the function in the interior. Okay, so there's a trick to figuring this out, say on the rectangle. And that trick is to use the superposition principle. We can use this to see that the solution is the sum of the solutions to 4 simpler boundary value problems, right? It's exactly the 4 you would think. All we're going to do is pick one of the boundaries and set all of the other boundary conditions equal to 0. So let's denote it like this. Let's start with the right boundary. Let's keep that one. So I'm going to put 0 boundary conditions everywhere else. And then here I'm going to put that this is equal to e of y. And then we're going to add the solution to, so now let's put 0 everywhere except at the top. So we'll put the boundary condition here. And then at the left boundary, we impose this boundary condition, but at all of the other boundary conditions, we impose 0 boundary condition. And then finally, suppose we put 0 boundary condition everywhere except at the bottom, right? So we now have 4 boundary value problems we need to solve, but these are much simpler than the one we started with. And if we take the solution to each of these, add them together, we'll end up with something that solves this equation. So that's because this PDE that we want to solve is linear and homogeneous. And the boundary conditions that we're looking at are also linear. And so it works fine to just add solutions to get a solution. Okay. So I'm going to show you how to solve the first one of these. The other ones are very similar, and I'll let you solve those. So let's consider the first one. As usual, it won't surprise you that we're going to start by finding all separable solutions. So let's look for u of xy given by capital X of x times capital Y of y. Right? And when we're looking for the separable solutions, we're going to impose all of the homogeneous boundary conditions. We're going to ignore this boundary condition for now until we've found all of the separable ones, and then we're going to sum a series, and only when we have that series do we consider this last boundary condition. Okay, so what does the equation look like for a separable solution? We would have 2 derivatives with respect to x plus 2 derivatives with respect to y. So that would look like x double prime of x times y of y plus x of x times y double prime of y. And we want that to be equal to 0. So if I put all of the x's on one side and all of the y's on the other, I end up with capital X double prime over capital X. is equal to minus capital Y double prime divided by capital Y. Right? I'm only interested in the non-zero solutions. So then x and y are non-zero and it's okay to divide. Now we do our usual thing. We stare at this. This side only depends on x and this side only depends on y. That means that this side only depends on y, but that means that it doesn't depend on anything, so it's a constant. And similarly, this side has to be a constant. So let's call that constant lambda. And now let's impose the homogeneous boundary conditions on y. So then y satisfies the boundary value problem. Y double prime is equal to minus y double prime is equal to lambda y. Y of 0 is equal to 0. Y of b is equal to 0. Right? And this is a boundary value problem that we've now come across many times. We recognize this as the eigenvalue problem. That leads to the Fourier sine series. So we know that the eigenvalues are n pi over L squared when n goes from 1, 2, and so on. And capital Y is a multiple of sine of n pi over L, but in this case, L is b, times y. So next we should solve. So now we look at the x, and from up here, right, we see that x double prime is equal to lambda times x. Notice that the y had a minus sign, but the x does not. So that's going to be different. And we're only going to impose the homogeneous boundary condition. So x of 0 is equal to 0. Right, so for now, we only impose the homogeneous boundary condition. We save the other one for later. The general solution to this equation is capital X is equal to some constant times e to the, so here with lambda equal to n pi over L squared. So then we would get n pi over L times x plus some constant times e to the minus n pi over L times x. Right? And the boundary condition, x of 0 is equal to capital E plus capital F, and we need that to be 0. So capital X is a multiple of e to the n, well, let's say it's a multiple of 1/2 of e to the n pi over L x minus e to the minus n pi over L x. So it's a multiple of this, and so it's also a multiple of 1/2 of this. And the reason I put the 1/2 is that this then has a name. This is the hyperbolic sine of n pi over Lx. Right? Thus, the series solution to the equation is u of x comma y is the infinite sum, n goes from 1 to infinity, of some constant. Let's go with alpha n of hyperbolic sine of n pi over Lx times the trigonometric sine, L is equal to b, times the trigonometric sine of n pi over b times y. Now we use the final boundary condition to find the value of the coefficients alpha n. All right, so the final boundary condition, if I scroll up, right, is this: u of a y should be e of y. So u of a comma y. So if we plug that into the series, that's the sum n goes from 1 to infinity of alpha n hyperbolic sine of n pi over b of a, and then sine of n pi over b y. And we want that to be equal to capital E of y. Okay, so if we write the Fourier sine series of E of y as the sum n goes from 1 to infinity of epsilon n sine of n pi over by, then we see that alpha n should be epsilon n divided by hyperbolic sine of n pi over ba, right? Notice that since n pi over ba is positive, hyperbolic sine of that number is not equal to 0, so that makes sense, right? Said differently, we can write alpha n as 1 over hyperbolic sine of n pi over ba times, well, we know what the coefficients of the Fourier sine series are, so it would just be 2 over b times the integral from 0 to b of the function e of y times sine of n pi over by dy. Okay, as I mentioned, the other simple boundary value problems can be solved similarly. Right? And I encourage you to work out on your own the solutions to these boundary value problems, which you can then add to find the solution to this boundary value problem. Okay, I want to do one more solution of Laplace's equation. Let's consider the Dirichlet problem for the Laplace equation on the unit disk. Right, so the unit disk, I'll denote with this blackboard bold D. So this refers to all of the points x, y, where x squared plus y squared is less than or equal to 1. right? So this is in R2. You just have the unit circle and you fill it in. So let's consider Laplace's equation, d squared u dx, d squared u by dx squared plus d squared u by dy squared equal to 0 on the unit disk. Subject to the boundary condition that u should equal f of theta on the boundary circle. Okay, so as usual, when you're working with the unit disk, you want to use polar coordinates. Right, so x is going to be r cosine theta, y is going to be r sine theta, right? Which is same as saying that r is equal to square root of x squared plus y squared, and theta is equal to arctan of y over x. Here, r varies between 0 and 1, and theta is going to vary between minus theta and theta, minus pi and pi. A computation using the chain rule very similar to what we did for the wave equation last time, shows that the Laplacian, so this d squared u by dx squared plus d squared u by dy squared, if you write that in polar coordinates, you get two derivatives with respect to r plus 1 over r times one derivative with respect to r plus 1 over r squared times two derivatives with respect to theta. And then we want to set that equal to 0. Okay, so let's now look for separable solutions but separable solutions in polar coordinates. So it's going to be capital R of little r times capital T of theta. So what does our equation look like? We have, right, two derivatives with respect to r squared plus 1 over r, one derivative with respect to r plus 1 over r squared, two derivatives with respect to theta. Right? If we plug in our guess for a separable solution, then we end up with r double prime of little r times capital T plus 1 over r times r prime plus two derivatives of t divided by r squared. Right, and we want that equal to 0. So we could rewrite that by putting all of the r's on one side and all of the thetas on the other. So let's write that as little r squared divided by capital R of r times r double prime plus 1 over r capital R prime equals minus t double prime of theta divided by capital T of theta. And now when you do our usual analysis, we say that this side only depends on r, and this side only depends on theta. But if they're equal, that means neither one depends on anything. They're both equal to a constant. Let's call that constant lambda. Okay, so first let's consider the equation for capital T. Since capital T of theta is meant to be defined on a circle, it needs to be periodic. And so it satisfies minus t double prime of theta equals lambda t of theta. And then I'm going to impose that t of minus pi is the same as t of pi, and the same for the derivative. T prime of minus pi should be equal to t of pi, t prime of pi. Right? And again, that's because it's defined on the circle, and so it has to match up at minus pi and pi. Right? Now we recognize this. As the boundary value problem. That leads to the Fourier series. Okay, hence we know that lambda is equal to n squared with n equal to 0, 1, 2, and so on. And that t of theta is a linear combination of cosine n theta and sine n theta. Okay. Next, let's consider the equation for r when lambda is equal to n squared. Okay, so let's see. We had this equation, right? And so for r, that means that r double prime of little r plus 1 over r prime of r is equal to n squared divided by r squared, capital R of r. Or if I multiply through by little r squared, I get r squared big R double prime plus little r times big R prime is equal to n squared capital R. Okay, so there's a really nice trick we can use. Notice that here what happens is that I take two derivatives, but I multiply by 2 powers of r. I take one derivative and I multiply by 1 power of r. And then here I take no derivatives and I multiply by no powers of r. So we can take advantage of that match. And make the very useful substitution right? If we set r equal to e to the z, then the derivative with respect to z, right, by the chain rule would be the same as the derivative of r with respect to c times the derivative with respect to r, right? The derivative of r with respect to c is just e to the z again, and that's just r. So that's r d by dr. Right? So this is what makes this a really good substitution to make, because here we notice that you're multiplying by the same power of r as you're taking derivatives. And here, that's what this does. It takes one derivative with respect to r, but it also multiplies by r, right? So I'm going to rewrite this, though, as the derivative with respect to r is equal to e to the minus z times the derivative with respect to z, right? So I'm just moving this r to the other side. So it would be 1 over r, but r is e to the c, so that's e to the minus z times d by dz, right? And I'm just doing that for ease of substitution. So now if I make this change over here, this equation becomes, like this equation, I have r squared, that r squared is e to the minus 2z, and then I have two derivatives with respect to r, right? So that's e to the minus z d by dz applied to e to the minus z d by dz applied to r, right? And then here I have r, so that's e to the z times the derivative with respect to r, which is e to the minus z times the derivative with respect to z. And that's all m squared r to the z. Okay, so what do we get here? So this is e to the minus 2z, and then there's going to be, when this d to the dz hits the e to the minus c, I'm going to get a minus e to the minus c, so I'll end up with minus e to the minus 2z times r prime, well, derivative of r with respect to z, and then plus, when this derivative doesn't hit the e to the c, so this comes out, and I end up with e to the minus 2z times two derivatives of r with respect to c. And then plus here, this e to the z and e to the minus c cancel, so I end up with just one derivative with respect to z. Okay, now here, when I multiply this out, this is going to, this r squared is e to the plus 2c. So this is going to cancel off these terms. And so I just end up with this minus one derivative, which cancels off this plus one derivative. So altogether, I end up with two derivatives of r with respect to z is equal to n squared r. Okay, so now this is a very simple equation. Right, because it's linear with constant coefficient, ODE. So the general solution is r of z equals, well, if n is equal to 0, you get a plus bz. If n is equal to 0, and otherwise you get a e to the nz plus b e to the minus nz if n is positive, right? Or if I switch back to the variable r, then this capital R of little r is equal to a plus b times log of z. This is if n is equal to 0, and then a r to the n plus b r to the minus n if n is greater than 0. Now, looking back at our problem, right, we're looking for a function on the disk, and we switch the polar coordinates, so r equal to 0 corresponds to the origin, right? So we want capital R to be continuous at little r equal to 0. So we don't allow the natural log term or r to the minus n. Thus, the general separable solution is r times capital T would be equal to, say, A0 if for lambda equal to 0, and an r to the n cosine n theta plus bn r to the n sine of n theta. So this would be for lambda equal to 0, and this would be for lambda equal to n squared with n positive. And summing these, we get u of r comma theta equal to a0 plus the sum n goes from 1 to infinity of an r to the n cosine n theta plus bn r to the n sine of n theta. Right, and except for the r to the n's, this looks exactly like the Fourier series expansion of some function, right? So again, that's not too surprising because we did notice that the boundary value problem we ended up with for capital T was the same boundary value problem that you end up with for the Fourier series. So returning to our problem, right, where we want to satisfy Laplace's equation on the unit disk with u equal to f of theta at r equal to 1. The solution is u of r theta is a0 plus the sum n goes from 1 to infinity of an r to the n cosine n theta plus bn r to the n sine of n theta, where a0, an, bn are the coefficients in the Fourier series of f theta, right? Because when r is equal to 1, right, then it's like this r to the n is not even there. And for this to match f of theta, well, that's just a Fourier series of f of theta, right? Of course, we have formulas for them. So a0 would be 1 over 2 pi, the integral from minus pi to pi of f of theta d theta. An would be 1 over pi, integral from minus pi to pi, f of theta times cosine of n theta when n is positive, and bn would be 1 over pi, integral from minus pi to pi, f of theta sine of n theta. Okay, and we will stop there.